tides. And we'll talk about deltas too. So why do we have tides? Well, if you've ever been to the beach, you notice that the water comes in, tide goes out. In a lot of places on Earth, that usually happens twice a day. And so this is the reason why. So the Earth and the Earth's oceans are attracted by the gravity of the moon and sun. So the moon is fairly close to Earth, so we could see the moon here, and it exerts a force, so it's pulling the ocean water and it's kind of pulling the Earth. And so we get a bulge, right, in line with the moon. We get a bulge on this side and on the opposite side. So as the Earth rotates, if you're at a point on the Earth, you're going to rotate into the bulge here, and so you're at high tide, and then you rotate out of that bulge and you're at low tide, and then you rotate into the next one, high tide, low tide. So one rotation, you usually have 2 high tides and 2 low tides. Now we have 2 situations here. We have spring tides on the lower left, and these occur when we have a full moon and a new moon. So what happens is the moon is in line with the sun, right? The orientation is the same. And that's why we see, the full disk of the moon, or we see the dark moon. And so the moon is pulling, but the sun also exerts gravitational pull on the Earth as well. So if they're pulling in the same direction, we have a higher high tide and a lower low tide. So you're rotating into both the moon and the lunar and solar tide, high tide, and then out of them and into them and out of them. So in spring tide, you have a bigger difference between high tide and low tide. Now, at the quarter moon, when we see half the moon's disk illuminated, in the first quarter and third quarter moons, now the moon is pulling at right angles to the direction that the sun is pulling. Now the sun, of course, is huge, so it has a bigger gravitational pull, but it's also farther away, so it affects the Earth less. The moon is closer, so it has a bigger effect on the tides. So the high tide is the lunar tide, right? So we rotate into and out of that high tide. But the sun tide, the solar tide here, is also pulling. So there's less of a difference between a high tide and a low tide in neap tide. You still have 2 high tides and 2 low tides a day, but there's less of a difference. Here's just another illustration. So here's a spring tide. The moon and the sun are both pulling in the same orientation. So if you were rotating on the Earth, you'd rotate into the high tide, into the low tide, high tide, low tide. Here's the neap tide. So here the sun is pulling this way, the moon is pulling at 90 degrees to that, so there's still a low tide and a high tide, but much less of a difference. But the tides, how big a tide is, also matters on the shape of the coastline too. So here's the Bay of Fundy. This is between Maine, New Brunswick, and Nova Scotia. And as the Earth rotates, this acts as sort of like a big funnel, and ocean water can get swept up in here, and so you have a really high tide, and then as it drains out, you have a really low tide, and so you can see the big difference in those pictures there. So tides, right? So with tides, the water's moving basically perpendicular to the shoreline. It's coming in or out. And so we get all sorts of interesting things like tidal deltas as water kind of rushes in to this area between a barrier island and a lagoon. It shapes channels perpendicular to the shoreline. So what you're going to do for this next at-home activity is you're going to look at a bunch of rivers using Google Earth, or you can use an atlas even, maps. And you're going to classify them as either river dominated, so we can see up at the top here, river dominated, tide dominated, or wave dominated, or most rivers are some mixture in between. So with a river dominated delta, this is where the river's dumping a lot of sediment into the ocean, and it's building out, and it's not getting sculpted by either wave or tide action very much. So you get this long bird foot looking delta. With a river that's tide dominated, most of the motion is upriver and downriver. So any little islands or sandbars or anything in the delta, you're going to have wide channels in between them, and they're going to be oriented upriver, downriver, because that's the main motion of the water driven by the tide. And if a river is wave dominated, any of that sediment that's dumped into the ocean is then going to get sculpted along the shoreline by longshore drift. So that's where you have really strong wave action that sculpts the activity by longshore drift. So what you're going to do is you have, I think, 10 rivers from the world, and you're going to see where they fall on this little triangular chart. Are they wave dominated, tide dominated, river dominated, or are they a mixture of both? So for instance, here we can see the Mahakam River. It's built way out from the shoreline. That means the river's dumping a lot of sediment and it's building that delta way out. So that's river dominated. But you can see those big channels in between. And so there's also a lot of tide action sculpting them. So the Mahakam River would be somewhere right in here. Oops. Somewhere right in here. That would be a combination of river and tide dominated. So your assignment is to go to Google Earth right here and look at some of these rivers and tell me if they're river or tide dominated, or river, tide, or wave dominated. So here's again the Mississippi, classic river dominated. It's building out, not a lot of sculpting of that shoreline by wave or by tides. If we go someplace like the Nile River, over here's the Nile Delta, we can see the river is building a pretty big delta out. It's projecting out into the Mediterranean Sea, but look at how smooth that coastline is. That's smooth because of longshore drift. And in fact, if we zoom in here, we'll probably see, yeah, there's some jetties that have been built here to combat the longshore drift here and keep this marina open. So look for stuff like that. Is it wave dominated? Is it tide dominated? Or is it river dominated?